I want to say a couple of words about modeling the chemical reactions. Well, not often, but sometimes we are dealing with flows that are coupled with some chemical reactions. This might be combustion, this might be biomass gasification, but not only. You can also see as a very, very special case of chemical reactions, you can see physical processes like, for example, evaporation, where you do have some kinetics of the process and you do have the transport of the species. It's a large word in this case, but simply of the water vapor that is transported with the fluid. So let me start with the general form of the chemical reaction equation. Let's assume that we've got component A plus component B. Uppercase A and B denote components, lowercase a and b denotes stoichiometric coefficients in the equation. Then one remark, remember that very, very often you will see reactions that are written just in one way, but the reality is that you cannot implement them in the CFD code in just one direction. Because really how it works, I'm not a chemist, but how it works chemically, you are turning the substrates into the products, but actually the chemical reaction stops when it reaches some equilibrium. And equilibrium is when some products are colliding and the reaction goes the other way around and the substrates are colliding. And the products are produced. So you need to remember implementing the chemical reactions in both sides and for given thermodynamic conditions, temperature, etc. Certain chemical equilibrium will be something that you observe macroscopically. So let's say these are the products. And the first thing that should be defined is the V. This will be rate of the chemical reaction, and simply defined as, it can be defined by each of these components, but I think it's easiest to remember that the rate of the chemical reaction is how quickly you produce the products. So let me start with that. You divide it typically by the stoichiometric coefficient, but the idea is that the rate, the chemical reaction, is how quickly, with respect to time, you are generating the C component. This one does not change anything if you've got like the, let's say, reaction H2O to H2O. Then the stoichiometric coefficient is 1. You will see that this one denotes exactly how quickly you generate moles of water vapor. The stoichiometric coefficient, like I would say, matter of definition. But if this one is produced, then clearly with the same rate, the substrates must vanish. So you can write it's minus 1 over A times the time derivative, the production of A. This might be the same as vanishing of B. And no wonder okay, understandable. All right, so let's move on. It's the definition. Right now, you need to know if you've got a certain number of moles of your substances. You need to know how quickly this reaction will really go. And the equation that is used in chemistry to calculate that you got some coefficient K times number of moles of component A to the power of alpha times number of moles of the component B times beta. And that's it. Like, depending on how much A is available, how much B is available, they are like moving randomly across space. If it's a gas, well, in the liquid probably a bit differently, but maybe not so, the distances might be not so large, but they are also moving randomly. When they collide, then you get some probability that the reaction will take place. So basically, the rate of chemical reaction is proportional to the availability of alpha and of A and B and the probability of their collisions. Alpha and beta coefficients. Depending on what the numbers here are, this defines the chemical reaction order. I cannot give you many examples on that. In majority of chemical reactions mechanisms, very, very often it happens that alpha and beta are just one, very, very often. I would say in the chemical reaction mechanisms that I have seen, really not very often I have seen reactions that you take something to the power of 2 or something like that. Additionally, the coefficients do not need to be whole numbers. This might be fractions. How you should deal with that? I think if you're interested in implementing any chemical reaction, you need to look in the literature for proper coefficients and proper reaction mechanism, because, well, this one you probably know from high school chemistry, but I think even if you split that into really physical mechanism, how the subsequent particles split, collide, etc., it's not that simple. They just, I don't know, because I'm not a chemist, but I think they're like losing some electrons, you've got some electrons, something. So there are many, many more collisions that sum up to such a reaction. So it's not the full reaction mechanism, but I think in many CFD simplifications you would simply implement such a straightforward equation, chemical equation. But if you want to get into the details, sometimes you're really dealing with the physical mechanism, how they split, how they collide, what can be coupled with what, etc. And this could split into a couple of equations. Anyway, if you want to implement that, you will not come up with the reaction mechanism on your own, at least with the background that we have, and you will not know the proper physical parameters for these reactions without finding the chemical reactions mechanism in the literature, in the scientific papers, or in the books. Or a good reference for you for looking for thermochemical properties of components might be the Janov tables. Really a huge collection of, I think, like 1,000 pages of data, formation enthalpies, heat capacities for many, many components, from temperatures ranging from, I think, almost 0 Kelvin up to, I think, 2,000, 5,000 Kelvin or something like that. It's a really huge collection of thermochemical properties. Well, this one should be supplemented with rate of the reverse reaction in the other direction. Then we've got C to, let's say, power of gamma times D to the power of delta. Where do you take this one from? This one is something that is very, very often, or always, I haven't seen other cases, calculated from the Arrhenius equation. The Arrhenius equation says that it's some constant A, the pre-exponential factor, times the exponent minus activation energy divided by universal gas constant. This one is called activation energy. And that's nothing else than simply temperature. Generally, for pre-exponential factor. Should I write it down? No. Okay. It's a pre-exponential factor. Basically, when implementing any kind of chemical reaction for each reaction, and you may have a couple, or 15, sometimes 50 reactions in your chemical reactions mechanism. For each reaction, you need to find the pre-exponential factor, and you need to find the activation energy of this particular reaction. These are the things that you will not move forward without. This one introduces really strong correlation with temperature. So you will see that until a certain temperature level, there will be reactions that are not activated before a certain temperature level is achieved. So that's why if you've got probably something like this, and you calculate it for the temperature and for the room temperature, I don't know what the chemical reaction rate will be, but probably something like 10 to the power of minus 12, or maybe even lower. If you take 3000 Kelvin, probably you will see that, yeah, it takes place. Questions so far? No questions. Then I've got a question to you. Okay, is the theory for one or a couple of chemical reactions? How do you use it in a CFD simulation? What do you think is needed?
Before, I have actually one question. How do we compute the KR? It's like it's K
from another level.
Yeah. Ah, okay. From the
same way.
Okay.
We just look up for the A and activation and energy for the other reaction.
Okay.
So maybe we can implement the transport equations for the species and add source terms that account for creation or destruction of the chemical components.
Very, very good. Let me rephrase. You actually don't change anything in the modeling of the flow. If you're modeling the flow with let's say, Navier-Stokes equations, well, okay, during our course, we covered mainly the incompressible Navier-Stokes. If you're dealing with chemical reactions, this means that probably temperature changes, so density changes. So with very, very small exceptions, but generally you cannot be modeling chemical reactions within this scope of incompressible Navier-Stokes equations. You would probably be able to do something like that for liquids. But for gases, generally, you need to cope with compressible Navier-Stokes equations. But then, generally, nothing changes to your Navier-Stokes equation. You're solving for the whole mixture, the flow of the mixture of gases. What changes is what you have is you've got the mass conservation equation. And what you need to add, and what Łukasz said, we are adding additional transport equations for each of the species. What would be species here? It would be H2, O2, H2O. So you're either, okay, let me say it wrongly at the beginning. So you're adding an advection diffusion equation for each species. So let's say we would have, well, you need to play around with the coefficients. Let's say we've got some concentration. Concentration could be, you can define it in moles per cubic meter. You can define it as kilograms per cubic meter. Like, it doesn't matter so much, but you need to be consistent. This concentration of, let's say, H2 with respect to time plus divergence of the concentration of H2 times velocity. You've got just one velocity of the mixture of all gases. You haven't got distinct velocities for each component, for each element. What else? You've got some diffusivity constant times the concentration, gradient of concentration of H2, plus you've got some, let me call it, or maybe S, the source term.
Is the mass conservation always true in chemical reactions?
Is it true? Like, yeah, yes, it's always true.
Like, because in radioactive...
Okay, but only in radioactive materials it's not. It's not true, although, you know, the differences are so small that, well, I have never been modeling the radioactive reactions in CFD, but I would guess even in radioactive reactions, maybe you don't even account for the change in mass because it's really extremely low compared to the energy that you produce. So maybe you still keep the mass constant and you only add energy that is produced in the reaction. Yeah?
I believe that we also have to take into account energy equation.
We need to.
And the other thing, I think that we have to take into account advection diffusion reaction equation only for n-1 species.
Yeah, that's one of the remarks that I wanted to make in a minute.
Sorry. And one question: are there any source term for Negros equation for some reactions? Because, well, I'm not sure, but can a reaction like produce momentum?
You know, for some reactions, it's a very tricky way of asking the question. I think no.
Okay, I think it can create momentum by like creating like some energy and large pressure somewhere, and
yeah, but you just added it to the energy equation.
Yes, yeah, but I have also a question. Shouldn't we consider in the advection and diffusion also the density in the terms, because the concentration and the density can change of each species, and
You know, I don't want to give you here the very complete set of equations that you can just take away and implement right now. I think this can be defined both for concentrations. This can be, and probably more convenient, this can be defined for densities, like in kilograms per cubic meter of each element. What I want to underline is that you need to have such a transport equation for the H2, O2, maybe H2O component, but in most cases, CFD codes are written in a way that you are writing one continuity equation for the whole mixture, and you're not writing equations for each element. You're writing these transport equations for n-1 elements. Say we would write it for H2 and O2, but we would say that concentration of H2O equals 1 minus concentration of H2 minus concentration of O2. And then this one is responsible for keeping mass constant in your whole system. These two equations for H2 and O2 are resolved, and H2O is chosen, is computed as the rest. This one must be properly selected. Like if you are dealing with some combustion simulations in the air, then you've got the you've got the how do you call the gases that do not, yeah, exactly, the inert gases. You've got the inert gases. In this case, the nitrogen N2 would be such a gas that does not go into the equations typically, and you've got huge amount of nitrogen in the air. So it's numerically, because of the numerical stability of the computations, it's best to select nitrogen as the strongest component to be computed as 1 minus the sum of the other ones, because then the relative error is the smallest. Yeah.
And also a practical note, because Konrad and I stumbled upon this problem once upon a time. The material which is used as the completion to one, the nth material, is not chosen by hand in a program like Fluid, for example, but when you're defining a mixture, I believe it's the last component you define.
Might be.
And you can very easily fall into a problem where the last material you defined was, for example, the oxidizer. And then when you're applying initial conditions to the simulation, you can, for example, start with a simulation where you have oxygen throughout the whole domain, and you wonder why you have temperatures of exceeding 10,000 Kelvin, for example. So be very wary of how these materials are sorted, what's the list, and what is the completion to one material. Saves a lot of time.
Yeah, and take that one of which you've got the largest amount in your mixture, because if you select it improperly, then you might run into numerical problems by having it almost zero in the physical world. So almost zero in the physical world means that if you've got some numerical errors, you might have 1 minus much, and that's already a bit less than 0. And it doesn't bring anything good to the physics, having negative concentrations. Energy equation needs to be added to the system, certainly. If you're dealing with turbines modeling, then this one, Schmidt number, exactly. This one, if we say that it's mass diffusivity, physical mass diffusivity, then this one needs to be changed by, let's say D physical mass diffusivity plus, in general, it is computed like turbulent viscosity turbulent viscosity divided by turbulent Schmidt number. And I think turbulent Schmidt number ranges from 0.2 to 0.5, more or less. Typically, a value in between, somewhere in between, is used for the whole computation. And this accounts for turbulent mixing of the mass of the species. One last thing that, to be honest, I'm not sure of. I have understood it twice or 3 times in my life when I needed that, but I'm not fluent. It takes a couple of, when I'm not dealing with it, it takes usually a couple of hours to go through all the equations and derivations to understand and be absolutely sure. But there is one vital question. Do you add an energy source to the energy equation? You basically write it for the enthalpies, because enthalpies are the best way to represent thermal energy and the energy of the chemical bonds. So basically the chemical energy that is included in the chemical bonds in such an element or such an element. To be honest, I never remember this without checking, because by intuition it seems to be intuitive that once you've got chemical reactions and you know from like macroscopic calculations that you do in heat transfer, combustion, etc., that you should add the calorific value of the reaction times the reaction rate and add it to the energy equation. But I'm not sure of it at the moment, but as far as I remember, I think it's wrong. You don't need to add any source terms to the energy equation. Why is it? It's because if you properly define the enthalpy of each of the components, then enthalpy of each of the components should include the chemical energy of the bonds plus thermal energy. So basically something like should be T reference TCP plus some enthalpy of formation, which already includes the energy in the bonds. And it turns out that the enthalpy of formation for H2 plus O2 is completely different than of that, because you've got different chemical bonds. And if you want for macroscopic reaction, if you want to calculate the calorific value, what you do, you basically subtract the enthalpies of formation of the products minus substrates, and you see how much energy the reaction produces. And as far as I remember, you don't need to put it into the energy equation in CFD, because, so to say, your procedure for calculating for the whole mixture, you've got something like, let's say, all the concentrations and temperature. This constitutes the total enthalpy in your mixture. So if the concentration changes, then, and the temperature changes, a completely different temperature should come from the different concentration, completely different composition of the mixture. But don't trust me. Like, if you're really going into the implementation something like that, go through the equations, go through a good book in modeling chemical reactions. I'm just making this remark for you so that you know what to be cautious about.
Okay. Excuse me, will you write just one equation for all the energy of all components?
Mhm.
and momentum.
Yeah.
Okay, so could you sum up just writing all the equations we use and all the variables we have to compute, just in order to sum
Mhm.
up and
Mhm.
show everything?
You should have the, let's assume, density of the mixture, velocity field, so 3 components of velocity, enthalpy, well, V is always for the mixture, enthalpy of the mixture, density of, well, taking from our example, H2, density of O2, and not taking the density of H2O. And that's it. Well, okay. One more thing, sorry. Pressure. Pressure will be one more variable in the system because you need to add ideal gas law to associate densities with enthalpy. So basically temperature that can be calculated out of it. And then pressure is yet another variable associated with this by relations of like thermodynamic relations.
And the concentrations are included into densities, or?
Yeah, let's say we got densities, not concentrations. Mm-hmm.
Do we have any hypothesis that the reaction is homogeneous?
What do you mean reactions homogeneous?
For example, those multiphases.
Yeah,
Okay.
we don't want to gas-solid reactions right now.
So, for example, when you're modeling like solid coal combustion, so first you're modeling the composition of the coal to the gases and then combustion of the gases. You're not modeling like combustion of the solid coal itself.
Or you can model solid coal as a fluid. Besides that, you've got like DPM.
You actually do that.
It's like DPM, and it helps you to like simulate combustion of some kind of liquid fuel or coal if it's quite small, without solving for multiplies.
For example, two fluids that create a gas.
Sorry, could you repeat?
Two liquids that create a gas.
Don't do simulations like that.
Yeah, just. Well, I believe that this would be hard with the DPMs, but you can check it. I'm not sure.
Yeah, we can talk later.
Yeah, we can talk later. Exactly.
But what we've been doing at these combustion simulations in the furnace, basically we had a trick. We had a special code which was able to, we had coal lying on the grate, flow of air, of fresh air from the bottom. So what we've been doing is we have written special code that was able to calculate the combustion of the solid on the grate, calculate the temperature of the gas right above the grate. So the temperature of the gas that goes from here, the composition of the gas, well, and basically it. And we've been omitting this subdomain in the CFD simulation at all. We have just been imposing the inflow boundary conditions with proper temperature, proper velocity of the gases, and proper composition of the gases. And then we've been modeling the homogeneous reactions of the gas components.
Well, at the beginning we were trying to use DPMs, but
so
working at all.
so
Just
numerically unstable that no.
It was better to write your own model in MATLAB than use NDPM.
Like if you really need to copy that, when it can be done, it works, but it takes a lot of time to make it run in a stable way. So if you've got reasonable assumptions how to simplify that, then better be not going into heterogeneous reactions. One last comment, or two last comments. This source term, I would say this one is the most important thing for modeling the chemical reactions. This means that you're basically taking this reaction rate equation with this Arrhenius relation to calculate how much, let's say, C will be, or H2 will be generated. But this means that if you've got a couple of reactions, some of them might generate H2, some of them might be using H2 to generate something else. So remember that S is like, you need to loop over your chemical equations and see, okay, in the first reaction, my H2 vanishes, so it would be probably like something like minus A exponent activation energy times what? Times this times this. If you've got two more reactions, maybe somewhere it's produced, then you would have plus the chemical reaction rate of the other reaction, etc. So the source term might be not very complex in the concept, but this might be a long one. And the second thing, a numerical remark. Generally, chemical kinetics, because we're dealing with chemical kinetics here, chemical kinetics is usually very, very fast, and different reactions have got different rates, often differing by a couple of orders of magnitude between each other. So numerically solving such a system results in having a so-called stiff system of equations. Stiff system of ordinary differential equations. And you usually need to have special procedures to solve stiff systems, because otherwise you need to use extremely low time steps. So low that is basically impossible to solve any real problem. So you need to have special procedures for stiff systems that can handle them, that can deal with them with larger time step sizes.
What are stiff systems?
The stiff systems are a very, very simple example of a stiff system would be
Boundary layer, like a flowing boundary layer. So you need to have, like, if you would like to have uniform mesh, you would need to have like verified mesh in the like whole domain, and
there is some similarity, but I wouldn't say it's this. The notion of a stiff system is associated with the time scale and the ordinary differential equations. You can imagine the following ordinary differential equation. Okay, if you take lambda, which is, let's say, 1, the solution, and you take the initial condition equals 1, then you would come up with the solution that looks like that in time. Now imagine that y is not a scalar function, it's the vector of just two components. And let's imagine that we've got y1, y2. You take the derivative of that. and you've got minus, and here you've got lambda 1, which is, say, 1, and lambda 2, which is 1,000. And you've got no coupling between the two components. What's the solution? The solution for y1 is obviously the same, but the solution for y2, it drops 1,000 times quicker, so it's basically something like that. And now imagine that you got some explicit procedure, numerical procedure to solve such a system. With just that, you could probably go with time step sizes like that, and you generate that. If you use such time step for the whole system, and you've got an explicit procedure, then you probably just generated something extremely unphysical, and you've got huge overshoot. So basically what stiff systems mean, it means that you've got huge difference in the time scale of the phenomena that are described by the system. You've got things that are that have got huge inertia and extremely low inertia.
What do you choose the time step? Because here we know the solutions.
One of the ways is to replace the explicit solvers by implicit solvers. It makes the situation stable or more stable. But obviously, it introduces some error. Don't know. Huge topic. There are some even MATLAB. You will find some. I think OD15S. S is for stiff systems, and there are a couple of procedures that can handle stiff ODs.